All right, so we're going to start by going over the homework. Question 12, the answer was Alleghenian. 13, 1.5 million years. 14, Mesozoic. 15, 57. 16, I don't know how to pronounce this. It's like elliptophilia. I don't know. It's the ELLIPTO1. And then 444, 23, Paleozoic. Number 20, something that says that birds were not around during the Ordovician, or birds came after the Ordovician, something like that. 21, the answer is Cloophysius. 22, Triassic. 23, Grenville. 24, you could have put either one of these three. They only asked for two, but Ordovician, Permian, or Devonian. Then 55.8, then 60, then 4,200 million years ago. For 28, it could have been something along the line. So I put extinctions. You could have just put changes in life on Earth, dramatic changes, something like that. 29 is 291, and 30 is Silurian, and I should have told you to skip 31. 32, the order would go grasses, birds, mammals, reptiles, sharks, insects, trilobites, stromatolites. Anybody want me to go over any on this page before we go ahead and flip it? Okay, so one thing I want to point out, be careful how you answer this. So like for question 14, it says name the geological era. So this has to be an era. This one says right here, which period? So then your answer has to be a period. So make sure you go through and you look at those. No one had any questions on this one? You didn't get anything wrong that you want me to go over? 14. Which era held the existence of the dinosaurs? So basically, which era were the dinosaurs around? So you could have done this a couple of different ways. You could have looked over at this line. So you see here that the dinosaurs were around from here to here. If you follow that over to the era column, that's the Mesozoic. Or you could have gone, here's where the earliest dinosaurs. Here's where they went extinct. Again, follow that over. That's the Mesozoic era. How about any more? Nobody? You guys got the rest of them right? Thank you, Kendra. 21. What would be considered a good index fossil from the Triassic period? So this was what we talked about on Wednesday, which was the last day I was here. So these are index fossils. Well, actually, these are index fossils. And these lines tell you, and these lines and circles tell you when those fossils were around. So it asked for the Triassic, right? Is that what it was? Yes, the Triassic period. So here's the Triassic. If I follow that over, there is only one letter for the entire Triassic period. So L, which you then match up down here, L is this dinosaur Cloophysius. So that is a good question because we only briefly talked about that on Wednesday. So that's the only index fossil that was around during the Triassic period. Good? Any more, guys? Those are good ones so far. 24, as I said. Who spoke? You. Thank you. 24. Yes, I had to go over this one with my last group. So it's to state two geological periods. So again, these are our only choices. So they had to come down the period column. With the northeast part of North America experienced a collision in the Phanerozoic eon. So now again, here's the Phanerozoic. Yes, it blows up, but we're only talking about above the black line. So anything above the black line is fair game. Where are we again? So we want the northeast part of North America experienced a collision, a continental collision. So remember, continental collisions, when two continents collide, they make mountains. These are any of these pictures or any of these spots where there's mountains. And if you read them, right here, the Taconian orogeny caused by closing of western part of the Iaptus Ocean and a collision between North America and a volcanic arc. So that's one continental collision. The Acanian orogeny caused by a collision in North America and Avalon and the remaining part of the Iaptus Ocean. So again, another collision. And this last one was the Allegheny orogeny caused by the collision of North America and Africa along the transform margin forming Pangea. So again, collision, collision, collision. So any of those, then you just read them over. Could have got the Ordovician, the Devonian, or the Permian. Really, I think that one, I've had to talk about that one every class period so far today. So I think that was just forgetting to look in that column. Any more? Okay, so those are the ones I wanted to go over anyway, so that's perfect. Let's go on to the back. So we've got number 33 was the bronchiopods. And then this one was erosion of the Acanian Mountains. And then for the multiple choice, we have 35, the answer was 4. 36, the answer is 3. 37, the answer is 3. 38, we have 4. 39 is 1, and 40 is 1. Are there any of those you want me to go over? Yeah, 40. This is a good one because this is the kind of stuff they love because you have to look on like 3 different reference tables all at once. So it says the diagram to the right. So this guy that reminds me of a pile of poop, which is not, but that's what it reminds me of, is an index fossil found on the surface bedrock of some parts of New York State, in which New York State landscape region is this gastropod fossil found in the surface bedrock. So again, these are talking about the guys on the bottom of the reference table here. So this little creature matches up with W. So W is who we're talking about. So then you look up on the reference table and you see that W was hanging out. The only time W was ever found on Earth was during the Ordovician period. Now that doesn't answer the question because they asked where in New York State would we find this guy? So we got to find out where in New York State are there Ordovician rocks. When you hear something about New York State, you flip to the New York State map. And the New York Ordovician is the diagonal lines. So there aren't many diagonal lines. So right up here along the coast of Lake Ontario, up all around the coast, so over here to the eastern side, and there's a tiny bit of diagonal lines down here. But again, the question asks what landscape region? So then you got to remember this map shows you the landscape regions. So I had already starred these 4. So we've got the Allegheny Plateau, the Tug Hill Plateau, the Adirondack Mountains, and the Newark Lowlands. So we just have to see which one of those has diagonal lines. So the Allegheny Plateau down here by the bottom of New York State. So here's the bottom of New York State that has polka dots. So it's not the Allegheny Plateau. The Newark Lowlands a little tricky. The New York Lowlands is right near the bottom of New York State. Here's Long Island, and the Newark Lowlands are right there above Long Island. So here's Long Island right there above, not diagonal lines there. There are diagonal lines up here a little bit, but that's not the Newark Lowlands. So it's not that one. The Adirondack Mountains, these ones are pretty easy. They're in this corner, no diagonal lines. And the Tug Hill Plateau is just a little bit off the coast of Lake Ontario. So here's Lake Ontario, coast of Lake Ontario, diagonals. They love that stuff. It used 3 reference tables. They love it because technically you didn't have to know anything off the top of your head, but you had to flip 3 pages to do that one. So that's the kind of stuff they're going to ask you a lot. Or you're going to have to go searching the reference table for it. But remember, my hint was, if you're ever thinking like, why do I ever need to know this? And your answer is never, unless I'm on Jeopardy, then you look through your reference table. So if it's something that you will never, ever, 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 ever need to know again in the rest of your life, unless you're going to win the $1 million on Jeopardy, look through your reference table. Find it in there somewhere. I promise it's in there. Any more? Nobody? Nothing? Seriously? You did okay with 39? Everybody got it right? I would love to. Thanks for asking. 39 says, The presence of which index fossil in the surface bedrock most likely indicates that a forest environment once existed in this region. Now notice I circled forest in my key. What kind of things do you find in a forest nowadays? Okay, animals. What else? Trees. Okay, did you say green? What'd you say? Right, rain. Yeah, okay. So let's talk about living things. So animals, like little squirrels, bunny rabbits, bears, birds maybe, trees, plants. What do you not find in the forest? Fish, seashells, things like that. So the same is true today as it was 5 million years ago. You would find them still in the water, but we're talking about a legit forest. If you just go walking through the woods, you do not find a fish. Okay, I didn't say in the creek, I said in just the forest. So you got to think a little more black and white for me. Anyway, so what they're asking then is which one of these characters, which these things are index fossils. So anytime you hear the word index fossils, you go to the bottom of page 8 and 9. So again, here's index fossils. So they are labeled. These guys are index fossils. The key is to find these and see which one would live in a forest. And again, be careful. I kind of talked about the spelling of these things. A few of these things have similar looking names. Make sure you just spell it out correctly. So this ANEU one is this right here. It's this tree. Tree. Just keep that in mind. Then we have this CENT one. That's this shell thing. Do they live in forests? No, not typically. Then we have the CYST one. CYST. That's actually a coral. And if you didn't know what it was, you could look up here that U is a coral. So corals aren't in forests. And this last one, this BOT one, BOT, that's a fish. So out of those four, this is the most likely, the tree is the most likely to be found in a forest. Everybody's all good then with the rest, or is there any more you want me to go over? Yeah. 33. Which lived the longest geological time? Brachiopods, crinoids, dinosaurs, or corals? The easiest thing to do is look at these lines. So here's the brachiopods. And you can write on these. So if you want, okay, so there's brachiopods. Crinoids must be on one of these, then I'm guessing. Maybe. Am I lying? Oh, yep, right here. Crinoids, or however you pronounce it. Dinosaurs and corals. Wants to know which one was around the longest. So dinosaurs aren't it. Their line's pretty short. I'm going to come over here just so you can see. Dinosaurs got a pretty long, short line. The crinoids, I lost them. So theirs is a pretty long line. So are the corals. But the brachiopods win out. They're just a smidgen longer. Any more? Sure. All right, then I guess we're ready to keep going. I will point out there's going to be a quiz on this reference table on Wednesday. It's going to be all old Regents questions. You got to be able to answer any of the questions that we've done. So we've done quite a few questions on these. We started on page 4 with some questions. Page 5, 6, and 7 were all questions on the reference table about pages 8 and 9. You should be able to answer them. Now, knowing there's a quiz, does anybody have any more questions? Okay, then what we're going to do is we're going to skip ahead in your packet. We're going to go a little bit out of order from what I originally wanted to do. You could go to page 15. Page 15, you'll see is a reading. What I would like you to do is gently remove that reading so that you don't have to flip the pages. Now, if you were lucky enough to get the double-sided packet, you'll see this page next. If you have the single-sided packet, you'll see a blank sheet of paper. If that bothers you to have that blank sheet, you can also rip that out. If it doesn't bother you, just leave it where it is. And we're going to be going to page 17. So I want like page 15 and 17 both out in front of you. So you can rip 15 out gently so you don't destroy your packet, like rip the corner. Oh my gosh. Didn't even need to go for it. Okay, you did it. All right, so we got the reading and then this page next to it. What we're going to be doing, I'm going to read it for you. And what I want you to do while I'm reading is you're going to be looking for these phrases. So I can't say vocab words because some of them are vocab phrases. But basically, we're looking for the vocab words and their definition in the reading. I would like you to either underline or highlight the definitions as we're reading. Does anybody want me to hand them a highlighter? Not a single person? It's a load of baloney. Who's taking one? Anybody else? Oh, I think I'm a good thrower. You guys are all just bad catchers. Anybody else? Okay, whatever for the rest of you. So again, while I'm reading, you are looking for principle of original horizontality, principle of superposition. You're looking for faulted strata. I'll give you a hint on that one. Faulted is defined one place, strata is defined a different place. Then you're looking for intrusion and extrusion. So here's the reading. It says, sedimentary rock is usually deposited in layers. In some places, the layers are tilted rather than horizontal. The principle of original horizontality states that no matter the present angle orientation of the sedimentary layer, it is almost certain that the layers were deposited horizontally and were tilted after deposition. Much of stratigraphy, the study of strata, the rock layers, is based on something called the principle of superposition. That's a fancy name for when there are layers, the oldest layers are on the bottom and the youngest layers are on top. And then you can see the picture there. We have a cake and a drawing of some rock layers, and it says, layers of rock are built up like layers of a cake. Bakers make the bottom layer first, then the next layer on top, and so forth until it is done. However, the principle of superposition doesn't always apply. Wind, water, and glaciers can erode entire strata away and cause an unconformity, a buried erosional surface. And plate tectonic activity can break or fault, uplift or tilt older strata above nearby younger strata. A good example of this is the Lewis Thrust, an area of Glacier National Park that extends from Alberta to Montana. Their 160-kilometer long and 6-kilometer thick deposit of Paleozoic sediment lies on top of several strata that are hundreds of millions of years younger. What happened? Well, originally the strata looked pretty normal, but around 75 million years ago, tectonic activity along the Pacific coast of North America caused land in the western North America to thrust upward, creating the Rocky Mountains. In an area now known as the Lewis Thrust, these forces uplifted a big slab of Paleozoic rock and slid it 80 kilometers eastward before it finally came to rest over a layer of much younger rock. Another exemption to the principle of superposition is an intrusion. An intrusion happens when hot magma squeezes into rocks and zones of weaknesses. The magma cools as it passes heat energy to the nearby rock. It creates a zone of contact metamorphism around the entire intrusion. Because the magma is surrounded by pre-existing rock, the intrusion is younger than the surrounding rock. An extrusion is not an exemption to the principle of superposition, but is an important concept to understand in the world of stratigraphy. An extrusion occurs at the surface. It is external. While rock below the extrusion is changed by contact metamorphism, there is no rock on top to be changed. Sometimes geologists find a layer of igneous rock that has not changed the layer immediately above it. This is evidence that the layer above it was deposited after the lava cooled. All right, so hopefully you found the 5 words in there, and we can also talk about what the words sound like originally anyway, and maybe that will help us understand. What we're going to do is we're going to go through and we're going to give a definition for all 5. I'm going to model it with some Play-Doh for you, and then we're going to do a drawing. Now, normally in this class, I don't have you do drawings. I'm not a fan of drawing things just to make them look like put a picture with a word. So I don't usually use drawings, but I do when they're important. This is a concept that you'll have to visually understand just as much as you can just recite the words off the top of your head. All right, so let's give it a whirl. Principle of original horizontality was defined in the reading, but I think we can take apart the word itself. To me, this word sounds like a word the queen would use while drinking tea with her pinky in the air. Principle of original horizontality. Can you just pick it apart from its words? Original horizontality. It does talk about the way it was before, but so what was it before? What do you guys think? Original horizontality. What way were they originally? You got it. So guys, by the way, which way is horizontal? This is a good question that we better make sure you guys know. Horizontal. Yeah, do it with your arms, everybody. Horizontal is flat. In case you don't know that, the way to remember, the horizon. By the way, the horizon is where the sky meets the land, is a nice flat line. So if we were to talk about the principle of original horizontality, the best way to define this is no matter what they look like now, no matter what they look like now, the sedimentary layers were originally, horizontal. So no matter what they look like now, because they could be tilted or broken or folded. So no matter what they look like now, they were originally horizontal. I'll move this down so you guys can. No matter what they look like now, the sedimentary layers were originally horizontal. Now I want to add, guys, I'm not talking about an individual rock, like something that fit in your hand or even something the size of your head. I'm talking about huge layers that exist like all throughout Western New York or all through the Pioneer School District. So we're talking about huge slabs of rock. Let's add then the principle of superposition. We'll do that one right now too. What did it say in the reading? Principle of superposition. Okay, so how can we sum that up, guys? You got it. So when there are layers, when there are layers, the oldest layer is on the bottom, youngest on top. So when there are layers, you'll find the oldest layer on the bottom, the youngest layer on the top. This is common sense. We can think of this as your garbage can. So let's say your garbage gets taken out on Sunday night and you have a fresh start Monday morning for your garbage. You have an empty can in the kitchen. You throw away Monday's garbage. It hits the bottom of the can. Tuesday's garbage, where's Tuesday's garbage end up? On top of that. And then Wednesdays, and then Thursdays, then Fridays, then Saturdays, then Sundays. Let's think about this. Let's pretend you realize you threw out your retainer on Monday and you have to go looking for it. It is a lot of garbage. Where will you find your retainer if you threw it out on Monday? All the way on the bottom. But you threw out your $20 bill on Saturday. Where will you find that? Near the top. Okay, this is not a difficult concept. You guys do things all the time. Like if you'd like to think of something a little bit more yummy than the garbage with the cake, which layer of the cake was the oldest layer? The bottom. Now, of course, it's not that much older than the top layer, but it just was put there first. You can't put the top layer and then the bottom layer. You have to start with the bottom and build up. Let's talk about how this relates to sedimentary rocks. So first of all, how do sedimentary rocks form? Remember this chart? Who remembers how to read the sedimentary rock chart? How do you follow the arrows though? If I have sedimentary rocks, I don't want to know how they were formed. Read it backwards. So sediments get deposited, buried, compacted, and cemented together. So we just learned what sediments are. They're broken pieces of rocks from weathering and erosion, yes. So here's a bunch of sediments that are getting deposited. So I'm dropping them off by glaciers or by wind, so they get deposited, buried, cemented or packed together, so compacted. And now I just made a sedimentary rock layer out of sediments. What do you notice about this layer? Might have, apparently Play-Doh sticks to paper. I did not know that. Hang on. It does not come off like that. All right, so that, what the heck? Well, you guys could have warned me. I'm glad you enjoyed it. So this is what you got. So I got a nice flat layer just sitting there. Nice horizontal layer. Now, so what happens, do you think, over the next couple million years? What happens on top of that layer? Yeah, new sediments. So new sediments get deposited, depositing sediments. Okay, fast forward here. Okay, they got deposited. Now, because I don't want to mess up my Play-Doh, they also get compacted together. This would all be happening on top of that, but stress. Okay, nice new horizontal layer on top. What happens next? More layers. This happens again and again. And so you have more layers on top. So see how they get deposited horizontally, and again, they get squished off camera here. This would happen on top normally, but I can't because it'd mess up my Play-Doh. We've got nice horizontal layers. So you can see if you were to look at this from the side, does a little bit, as long if your cheeseburger was made out of black buns and stuff. But we've got nice horizontal-ish layers. So we need to draw this. Principle of original horizontality says that when the rock layers were formed, they were originally horizontal. So we just need to draw some horizontal rock layers. Now I am just going to lightly shade in a couple of these layers to make them look different than each other, but you don't have to. That is principle of original horizontality. Now what it's saying is, okay, so they were originally nice and flat, but what could happen to them in the meantime? No, they're not going to get squished together. They could get tilted, so two plates could come towards each other and they would tilt up. They could also get squished in between two plates and they could do what's called folding. But no matter what they look like now, so if they're tilted or folded, they were originally nice and flat. Now, principle of superposition just says when there are layers, the oldest one is the one on the bottom. So if you remember, I laid down my black layer first. So then it's sitting around there getting old. Then my yellow layer. And then I deposited the pink layer on top of that. How can I draw this concept? Same way, and what might I want to add to the same drawing? Label the oldest. So I'm going to literally draw the same exact drawing if I can. I'm not perfect here. Same exact drawing. I'm just going to label oldest on the bottom, youngest on top. So this is just showing that the first layer that gets set down is the oldest. The youngest layer is the one that gets set down last. So do you remember how we talked about absolute age versus relative age? Please tell me you at least remember those, the conversation. What am I talking about here then? Absolute or relative ages? Am I? I'm not. I'm putting them in a sequence. I am doing oldest to youngest. This is how you do relative age. I didn't say how old this black layer was. It's just the first one. Then the yellow one's the medium one. The pink layer is the youngest. So I'm not giving an exact age. I am just talking about how old they are compared to each other. All right, faulted strata. Did you find that in the reading? No, not at all. Now remember, I did say they were two. I got Play-Doh here too. Excuse me. I scratched some Play-Doh off my paper. Annoying. So in the reading, did anybody find the word strata? What's strata? It's defined, second paragraph. Much of stratigraphy, the study of strata, the rock layers. So what is strata? Rock layers. So strata is rock layers, and then fault was down here. Now this one's been throwing people off. It says, and plate tectonic can break, parentheses, fault. Can also uplift or tilt. So what is fault? It is right. So if we start here, let's start with strata, which we already talked about. That's the layers. The rock layers, and fault was to break. So what is faulted strata? Yep, so broken rock layers. And by the way, what is powerful enough to break rock layers? It said in the reading. Not other rocks. Guys, it said right in the reading. I literally just pointed to it. It's the only thing strong enough to break rocks. I think I hear it. Plate tectonic activity can break, fault, uplift, or tilt older rock layers above nearby younger rocks. So you do need to know that this is from plate tectonics. So again, plate tectonics can do a couple of things. Again, can't ruin the Play-Doh. So I had my beautiful rock layers. Plate tectonics can pull them apart. And then what do you see when you pull them apart? You can still see the bottom layer, the middle layer, and the top layer. So it could pull them apart. It could squish them together and stack them up so you've got oldest, medium, youngest on top of each other. Or it could even shuffle them like a pile of cards. So to draw this, what we're going to do is we're going to draw the first set of rocks here. So same layers I'm going with. But now, because of plate tectonics, there's going to be a big gap in these rocks. In this example, plate tectonics has pulled them apart. Now you could still match them up. Their oldest is there, youngest on top. This is what happened, remember when we talked about continental drift. Alfred Wagner was able to go and match up rock layers and see that here in the United States and way over in Europe, they could match up the rock layers. All right, I think that's going to be it for today. And we will get the last two here. You have no homework and we'll finish this up tomorrow.